All right, this is the Helicopter Flying Handbook, Chapter 11, page 14 of 24, low G conditions and mast bumping. Low acceleration of gravity, low G, or weightlessness maneuvers create specific hazards for helicopters, especially those with semi-rigid main rotor systems, because helicopters are primarily designed to be suspended from the main rotor in normal flight with only small variations from positive G load maneuvers. Since a helicopter low G maneuver departs from normal flight conditions, it may allow the airframe to exceed the manufacturer's design criteria. A low G condition could have disastrous results. The best way to prevent it from happening is to avoid the conditions in which it might occur. Low G conditions are not about the loss of thrust, rather than balance of forces. Helicopters are mostly designed to have weight, gravity pulling down to the earth, and lift opposing the force of gravity. Low G maneuvers occur when this balance is disturbed. An example of this would be placing the helicopter into a very steep dive. At the moment of pushover, the lift and thrust of the rotor is forward, whereas gravity is now vertical or straight down. Since the lift vector is no longer vertical and opposing the gravity or weight vector, the fuselage is now affected by the tail rotor thrust below the plane of the main rotor. This tail rotor thrust moment tends to make the helicopter fuselage tilt to the left. Pilots then apply right cyclic inputs to try to correct the left. For the left, since the main rotor system does not fully support the fuselage at this point, the fuselage continues to roll and the pilot applies more right cyclic until the rotor system strikes the mast bumping, often ending with unnecessary fatal results. In mast bumping, the rotor blade exceeds its flapping limits, causing the main rotor hub to bump into the rotor shaft. Figure 11-10. The main rotor hub contact with the mast usually becomes more violent with each successive flapping motion. This creates a greater flapping displacement and leads to structural failure. Yes. Structural failure to the rotor shaft. Since the mast is hollow, the structural failure manifests itself either as shaft failure with complete separation of the main rotor system from the helicopter, or a severely damaged rotor mast. In situations like the one described above, the helicopter pilot should first apply aft cyclic to bring the vectors into balance with lift up and gravity down. Since helicopter blades carry the helicopter and have limited motion attachment, care must be given to those attachment limits. Helicopter pilots should always adhere to maneuvering limitations stated in the RFM. There may be more than one reason or design criteria which limits the helicopter flight envelope. Heed all the manufacturer's limitations and advisory data. Failure to do so could lead to dire unintended consequences. So page 15 to 24, low rotor RPM and blade stall. As mentioned earlier, low rotor RPM during an auto rotation might result in less than successful maneuver. However, if rotor RPM decays to the point at which all rotor blades stall, the result is usually fatal, especially when it occurs at altitude. It can occur in a number of ways, such as simply rolling the throttle the wrong way, pulling more collective pitch than power available, or when operating at high density altitude. When the rotor RPM decreases, the blades produce less lift, so the pilot feels it's necessary to increase collective pitch to stop the descent or increase the climb. As the pitch increases, drag increases, which requires more power to keep the blades turning at the proper RPM. When power is no longer available to maintain RPM and therefore lift, the helicopter begins to descend. This changes the relative wind and further increases the angle of attack. At some point, the blades stall unless RPM is restored. As main rotor RPM decays, centrifugal force continues to lessen until the lift force overcomes the centrifugal force and folds or breaks the blades. At this point, airflow will provide no any lift or driving force for the system, and the result is disastrous. Even though there is a safety factor built into most helicopters, anytime rotor RPM falls below the green arc and there is power, simultaneously add power and add throttle and lower the collective. If in forward flight, gently apply aft cyclic causes more airflow through the rotor system and helps increase rotor RPM. If without power, immediately lower the collective and apply aft cyclic. Recovery from low rotor RPM. Under certain conditions of height of high weight, high temperature, or high density altitude, a pilot may get into a low rotor RPM situation. Although the pilot is using maximum throttle, the rotor RPM is low and lifting power of the main rotor blades is greatly diminished. In this situation, the main rotor blades have an angle of attack that has created so much drag that the engine power is not sufficient to maintain or attain normal operating RPM. When rotor RPM begins to decrease, it is essential to recover and maintain it. As soon as low rotor RPM condition is detected, apply additional throttle if it is available. If there is no throttle available, lower the collective. The amount of the collective can be lowered depending on altitude. Rotor RPM is life. If the engine RPM is too low, it cannot produce its rated power for the conditions because power generation is defined at the qualified RPM value. An RPM that is too low equals low power. Main rotor RPM must be maintained. When operating at altitude, the collective may need to be lowered only once to regain motor speed. If power is available, throttle can be added and collective raised. Once helicopter rotor blades cone excessively due to low rotor RPM, return the helicopter to the surface to allow the main rotor RPM to recover. Maintain precise landing gear alignment with the direction of travel in case a landing is necessary. Low inertia rotor systems can become unrecoverable in 2 seconds or less if the RPM is not regained immediately. Since the tail rotor is geared to the main rotor, main rotor RPM may prevent the tail rotor from producing enough thrust to maintain directional control. Pedal control is lost and the altitude is low enough that a landing can be accomplished before the turning rate increases dangerously. Slowly decrease collective pitch, maintain a level attitude with cyclic control, and land. All right. So we'll hold off there. That is page 15 of 24. Yeah, it goes 14 and 15 of 24. Low G conditions, mast bumping, low rotor RPM, recovery from low rotor RPM. And I'm going to go into page 16, system functions. That's chapter 11.